Okay, we saw in the last lecture that the most general form of the equations would be either difficult to solve numerically, and in addition, we would not receive too much understanding, too much insight if we just solve the equations numerically. So the strategy would be we simplify the problem, first of all, to get into a position to solve them really numerically, and secondly, to gain with a restricted system, with an approximated system, more insight into the physics. The first approximation we do is keeping as much of the physics as we can and simplify simply the geometry. Simplifying geometry is reducing the problem to one-dimensional system, a one-dimensional spherical system, by adopting spherical symmetry for our star and also for the motion and the dynamics of the star, and introduce spherical polar coordinates r, theta and phi, and all quantities will only depend on the radius r. In one-dimensional systems, it's convenient to adopt the Lagrangian description. This is not true for three-dimensional systems. That often the Eulerian description is more appropriate, but in one-dimensional systems, usually the Lagrangian description is more favored. Okay, so we adopt the Lagrangian description. And first of all, we introduce a new Lagrangian deep independent variable. So far we have taken the initial position vector of a mass element as the Lagrangian coordinate, rather than taking r0, which by r0 we describe the initial radius of our mass element as the Lagrangian variable. We consider the mass contained in a sphere of radius r as a variable. How is it done? Well, the mass inside a sphere of radius r, this would now be either r is now the Lagrangian dependent variable as a function of r0 and t, integrated. Mr is the integral of density over the volume element. The volume element in spherical coordinates would be 4 pi r squared dr. So we have to get the mass inside a sphere of radius r, we would have to integrate rho times 4 pi r squared dr from 0 to the actual position of our mass element r. Well, this is, of course, since we have mass conservation, this should be the same mass which is contained in the sphere of radius r0, because there is no way to lose mass once the radius of our mass element change. So this should be exactly the same mass which is obtained by integrating rho times 4 pi r squared dr in the initial position. So what we change is simply the radius from r0 to r. This is the actual radius and this is the initial radius, and the mass contained at time equals 0, contained in a sphere of radius r0, will be the same mass. It's denoted here with mr0, that should be equal. Because no mass can get lost or gained, this mr should be equal to mr0 should be equal to mr due to or as a consequence of mass conservation. So mass conservation is simply that this dmr by dt should be 0, or mr is equal to mr0. So instead of taking r0 as the Lagrangian variable, we could also equivalently use mr, which is mr0, mr equals to mr0 as a new Lagrangian variable. So this is time independent and it ensures mass conservation, and at the same time it replaces r0 as a Lagrangian variable. So it's replacing r0 with mr0, and mr0 is equal to mr. due to mass conservation. So this might be a new variable, a new Lagrangian variable. M is independent, and R, now the radius, where we can replace, or we can write the radius instead as a function of R0, like here. We can write the radius as a function of the Lagrangian variable mr and t as a dependent variable. Radius is now a dependent variable. The independent variable is mr, and it's a Lagrangian way of describing the system. Okay, there is actually a differential relation between the dependent variable r, the Lagrangian dependent variable, and the Lagrangian independent variable mr, simply by differentiating this integral with respect to the radius. So we get dmr by dr is simply the integrand, which is rho times 4 pi r squared. Okay, so we have a differential relation between depending variable r and independent variable mr in the Lagrangian picture, which is given by 4 pi r squared rho. This is simply the definition of mr. Or if we invert this relation, we can rewrite it in terms of dr by dmr. It's simply taking the 1 over dmr by dr, which leads to dr by dmr is now 1 over 4 pi r squared rho. And this relation might now be used to change between the variables r and mr, to transform from the variable radius to the variable mass. So to say, we are now going to change, or we can transform from the position as Eulerian position as an independent variable to the Lagrangian variable mr. So, and the transformation is given by dr by dmr. So d by dmr is 1 over 4 pi rho squared times d over dr. This might be used as a transformation from radius to mass. Yes?
What sort of advantage it gives when we go from this using independent variable R0 to the independent variable as mass?
You will see in a moment what will happen, how the equations can be simplified, and what the advantage is how we get a more convenient description. Okay. May I just ask for a few seconds? You will see it in a moment. Okay. First of all, of course, we are interested in gravity. Gravity, in an Eulerian sense, is given by the derivative of the potential with respect to r. R is now the Eulerian variable, and we have the equation which determines the potential, which is Poisson's equation. We drop the theta and phi terms because we assume spherical symmetry. So the radial part of Laplacian operators is d2 phi by dr squared plus 2 over r d phi by dr. All these derivatives with respect to theta and phi are 0 because we assume spherical symmetry. And according to Poisson's equation, this is 4 pi g times the density. Well, we rewrite it a little bit. This expression might be written as 1 over r squared d by dr of r squared d phi by dr. You can convince you immediately that these two expressions are the same. Okay, now we multiply the equation with r squared and integrate it. So we have, on the right hand side, we have 4 pi g rho times r squared integrated over dr. Then this should be r squared times d phi by dr. The right hand side is g times mr. just by definition of mr. Or we get the phi by dr, which is the gravity. In the equation of motion, only the gradient of the potential appears, so the gravitational force or the gravitational acceleration. The phi by dr is gmr over r squared. So we have the gravity, and this is the only point where the gravity appears in the equation of motion, is given in a closed algebraic form as gmr over r squared. mr is the independent Lagrangian variable, and r is the dependent Lagrangian variable. Whereas in the Eulerian picture, we would have to integrate this in a much more complicated way. So mr is, in the Eulerian sense, it's an integral, and it's difficult to deal with. Here in the Lagrangian sense, it's one of the variables. The Lagrangian way is just avoiding this integral and avoiding an additional integration. This is the advantage. One of the advantages to go to the Lagrangian picture and choose the mass as an independent Lagrangian variable. It's okay. Does it answer your question now? That's one of the advantages. We omit one integration or one differentiation. We reduce, so to say, the order of the differential system by having done already one of the integrations and using these integrated variables as one of the new variables. This is the trick. Okay, that's it. Okay, so the next assumption we go from the heat flux, which has only one component in the radial system. F theta and F phi are 0. There's only one component, which is the radial component of the flux, and replace it by the quantity which astronomers are used to, which is the luminosity. So in a spherically symmetric system, we can just get the luminosity, the energy per time which leaves the star or which goes through the star, by multiplying with the surface of a sphere times the flux per area and time which goes through the star. So we usually replace the flux by the luminosity. It can be done for a spherically symmetric system. Okay. Then we use pressure and temperature as the thermodynamic basis. That means we write the entropy as a function of pressure and temperature. Now I have to resort to some thermodynamic relations. Well, TdS is written now in the form that it's Cp, it's the specific heat at constant pressure, times the differential of the temperature, minus delta over rho times the differential of the pressure. Delta is defined. Now I have to introduce several thermodynamic quantities. Delta is the logarithmic derivative of density with respect to temperature at constant pressure, with a minus. And alpha, for completeness, is the logarithmic derivative of density with respect to pressure at constant temperature. We are probably not used to this notation. Why do we use logarithmic derivatives? What is a logarithmic derivative? Well, a logarithmic derivative is, or are you familiar with that? Okay. So logarithmic derivative means, well, if we have something like d rho over rho, this is d log rho, because d log rho is simply the derivative of log is 1 over. So this is 1 over rho times d rho. So all these quantities, d rho by d rho, can be written as d log rho. And logarithmic derivative means, for instance, let's take the logarithmic derivative here, alpha d log rho over d log rho over d log P at constant temperature is simply d rho by dP at constant temperature. This is familiar. This is the derivative of rho with respect to pressure at constant temperature, and to get a logarithmic one, it's P over rho. So this is dP over P is d log P, and d rho over rho is d log rho. Why do we use these quantities? First of all, they are dimensionless, because dimensions of rho, dimensions of P cancel, and they are dimensionless quantity, and usually logarithm is a small function, so they are of order unity. So we get, using this notation, these alphas and deltas are dimensionless quantities, and they are of order unity. So that's convenient, for instance, also for numerical computations. Okay, how do these quantities come? Where do they enter? They do enter if we write, for instance, rho as a function of pressure and temperature. So let us write now rho as a function of pressure and temperature. So we write rho is function of pressure and temperature, and we take the differential of it. Usually in thermodynamics you always work with differentials. So d rho is d rho by dP at constant temperature times dP plus d rho by dt at constant pressure dt. This is simply taking the differential of an unspecified relation of the type rho as a function of P and T. Now, how do these coefficients come about? We divide this equation by rho, and then d rho by d rho. So this will be 1 over rho here, 1 over rho, and we we rewrite in terms of dP over P. Then we have to write P here, and here we have a dt over t. Okay, we go to the relative changes, and what you have here then is d log rho by d log P at constant temperature. So this is d log rho by d log P at constant temperature, and this here is d log rho by d log T at constant pressure. And these coefficients are the alphas and deltas. So this is defined as alpha, and this is defined for convenience with a minus delta. This is the definition of these coefficients. We will come across many of these definitions. So for instance, if we write the opacity as a function of pressure and densities, we can do the same as for the density. Then we get d log kappa as a d log kappa by d log P, which is a kappa sub P, or d log kappa by d log T. This is kappa sub T. These are derivatives which are dimensionless and which are of order unity. So this is usually done for any quantity. What I have done here for the density might be done for the kappa as a function of P and T, or it might be done for the epsilon as a function of P and T. We define all these logarithmic derivatives in the same way. Okay? So if you are not yet familiar with that, this is how the thermodynamics is typically addressed in stellar physics. Okay, now I promised I would explain what is how this T times ds by dt is one of the terms which appears in the energy equation. How we replace this by Cp by times the time change of temperature and the time change of pressure. So we can, by this relation, replace the time derivative ds by dt, which appears in the energy equation, by the time derivative of the temperature and the time derivative of the pressure, which includes thermodynamic quantities like specific heat at constant pressure and this strange coefficient delta here. So we have to somehow prove this relation. Let's go back. Okay, what I already wrote down is here d rho might now be written as d rho by dp at constant temperature, dp plus d rho by dt at constant pressure times dt. And as done before, we go to the relative changes, which is d rho over rho, which is alpha times dp over p plus or no, minus delta times dt over t. Now we consider the entropy as a function of pressure and temperature. So we have in this way dq, the change of the heat content of our mass element, is given by T times ds. This is thermodynamics. The change of heat content is given by T times ds, and now we write ds in the same way as we did for the density. So we say ds is ds by dt at constant pressure dt, and plus T, of course, T times ds by dp at constant temperature dp. Okay, if we now consider heat transfer to our mass element at constant pressure, that constant pressure means dp is 0. So we have dq is equal to T times ds dt ds by dt at constant pressure dt. dp 0 means this term is 0 constant pressure. That means dq is something like dt. Well, if we change the heat, if we put heat into our system and the temperature changes and the pressure is 0, then the coefficient of the change of the temperature will be the specific heat at constant pressure. So what we have seen then, that the specific heat at constant pressure is simply one of the derivatives of the entropy with respect to temperature. So we have now seen by this experiment that Cp is T times ds by dt, and this is the first part I wanted to prove here. So T times ds is simply Cp times dt. There's the second term is left, which was minus delta over rho. So how do we prove that T times ds over dp is something like delta over rho? Well, it requires a little bit more effort. Okay. Well, let's go to the first law of thermodynamics. dq is the change of the internal energy minus p over rho squared times d rho. This is the pdv term, and this is the change of the internal energy. Now let's express du and d rho in the same way by dp and dt. So let us assume that the internal energy depends on pressure and temperature and also the density. We have done that already above. So this has been done for the density already. It's already done. Express it in terms of dp and dt and do the same for the internal energy. Okay, what are we left with? So this is du by dt at constant pressure times dt plus du by dp at constant temperature times dp. Now the same for the d rho. This is minus p over rho squared d rho by dt at constant pressure minus p over rho squared d rho by dp at constant temperature. Okay? Well, and now we compare our formulation in terms of the entropy derivatives with these derivatives. Okay, so let's go to the, oops. Okay. So dq is either in terms of the entropy given by these two terms, or it's given by these two terms. Now we take the coefficient of dt, and therefore t times ds by dt has to be equal to that bracket, and t times ds by dt has to be equal to that bracket. You agree? Okay, let's write it down. And what we are aiming at is determining this derivative. Okay. So we have two identifications. T times ds by dt is du by dt minus p over rho squared d rho by dt. And the second one is T times ds by dp is equal to du by dp at constant temperature minus p over rho squared d rho by dp at constant temperature. Two equations. And what we are doing now, we differentiate the first equation by pressure at constant temperature, and we differentiate the second one by the temperature at constant pressure, and subtract these two from each other. So differentiate the first by dp minus differentiate the second one by dt. Okay? What happens? For instance, take this term du by dt and times or differentiate it again by dp minus du by dp differentiated by dt. What is that? If you take the difference, it's 0. So these two terms cancel. Similarly, if we take if we ignore this temperature, if we differentiate this with respect to t and p minus differentiation with respect to p and t, these terms should cancel. So let's consider first the left-hand side. We differentiate this quantity with respect to temperature at constant pressure. Then we have we have to differentiate this with respect to pressure at constant temperature. If we differentiate temperature with respect to pressure at constant temperature, it's 0. Okay, this is 0, and the second one will cancel with that. And so this has to be differentiated with respect to pressure at constant. This has to be differentiated with respect to temperature at constant pressure. If you differentiate temperature with respect to temperature, it's 1. So we have what is left on the left-hand side in this differentiation and subtraction is minus ds by dp at constant temperature. That's the quantity we want to determine. Okay? So what we have on the left-hand side, what is left is minus ds by dp at constant temperature. Anything else cancels. We already saw that these cancels, and if we differentiate these by temperature and pressure and subtract the same term with differentiated with respect to pressure and temperature, so they will also cancel. So what is left is the differentiation of this p over rho squared, which is left. So we have, in this case, we have this term, it's minus d rho over dt by p, and here we have left this d rho over dp at constant pressure. We have to differentiate this quantity with respect to pressure. This gives first dp by dp is 1 over rho squared, which is left. And then we have to differentiate the 1 over rho squared, which gives minus 2 over rho cubed times d rho by dp at constant temperature. That's left here. The same is done here, and it has to be differentiated at constant pressure. So this term will not appear. This will be 0, and it's only the differentiation of 1 over rho squared which is left. And we have then the minus p 2 over rho cubed times d rho by dt at constant pressure. Okay, so what we are getting is Well, these two terms, d rho by dt times d rho by dp, we have here, and here we have d rho by dp times d rho by dt. This is identical. So these two terms cancel. And we are left only with minus d rho by dt at constant pressure times 1 over rho squared. Everything else is gone. Okay. What is left now? So minus ds by dp at constant temperature is given by minus d rho by dt times 1 over rho squared. Or if we rearrange it a little bit, then taking out the minus signs, T times ds by dp at constant temperature is given by T over rho times d rho over dt at constant pressure times 1 over rho. And this is simply, this term here is d log rho by d log t at constant pressure times 1 over rho. And according to the definition, this is minus delta over rho. So we have proven that this T times ds by dp at constant temperature is minus delta over rho. Okay, I've done this in extension because such calculations appear in stellar physics at any time. You have to transform back and forth, and you have to be aware of such calculations. So you have to get used to this formalism. Sorry about it. It was a little bit of algebra, but it was a little bit of helpful thermodynamics. Okay. So what we have proven now is that, first of all, this term is proportional to Cp. This is the specific heat at constant pressure, and this is something like minus delta over rho. Okay, so let's go back. Let's go back. TdS now we have proven can be written as Cp times dt minus delta over rho times dp. So we replace in the energy equation, we replace the derivative with time of the entropy by the derivative of time of temperature and pressure. This is one step which is done just to meet the usual notation. We could have stayed with the entropy as a variable, but usually people use temperature and pressure as the variables, and therefore the usual way or the conventional way to describe this energy equation is done in terms of temperature and pressure. This is just a tribute to the general convention. There's not much physics behind it, except for transforming between different thermodynamic bases. Okay, the next transformation which is done is taking the dr by dm, so to say the equivalent of the mass conservation, take this definition of the mass mr for a transformation from the Eulerian variable r to the Lagrangian variable mr. And of course, in this context here, dt, whenever we have d by dt, even if we write it as a del over del t, it's meant in the Lagrangian sense. We are fully in the Lagrangian scheme. So sorry about this. I would like to avoid confusion, but usually it's in stellar physics they use del by del t, even if it's a Lagrangian time derivative. Okay. So in this context, the del by del t refers to the Lagrangian time derivative. So what do we get in the end? We get the equations for spherically symmetric structure and dynamics of the star. We already saw the first one, which is simply the definition of the mass inside sphere of radius r. So you may regard here now r as the dependent variable, and mr is the Lagrangian independent variable, which is given by 1 over 4 pi r squared rho. You may regard this as as an expression for mass conservation. You could also say it's simply the definition of our mass coordinate or coordinate MR. What we are now doing, we replace the pressure gradient, which is appearing in the Euler's equation. We replace it dP by dr by dP by dmr using this as a transformation equation. So d by d, you just have to multiply d by dr by this expression, and then you automatically have the dP by dmr. You get this factor 1 over 4 pi r squared for the gravity. The gravity is now written as minus gm over r squared. If you multiply it with 1 over 4 pi rho squared, you get it 1 over 4 pi r to the fourth. The density is gone because there is a 1 over rho here, 1 over rho times the density, and the term left is the acceleration now, not in the Eulerian description, but in the Lagrangian description. In the Lagrangian description, it looks much simpler than in the Eulerian one. We don't have the v times nabla v term. Lagrangian term, we just have the acceleration. Okay. I think it's a simple way. I don't need to do this in detail. You have to transform from d by dr, the pressure gradient, using this transformation, and there is nothing else behind it. Okay? That's for the equation of motion, which becomes pretty simple here. Then we have, instead of the gradient of the temperature, instead of the divergence of the flux, we have the derivative. We replace the flux by the luminosity, and then the divergence of the flux may be written as the gradient of the luminosity. The gradient of the luminosity is again replaced by the gradient of the luminosity in terms of the mass coordinate. So we get dl by dmr instead of divergence of the flux, which is equal to the energy generation rate minus the T times ds by dt, and the T times ds by dt is now replaced by specific heat at constant pressure times the time derivative of the temperature plus delta over rho times dP by dt. Okay, so this is the derivative of the entropy, and it's the dq. This is the divergence of the flux, and this is the energy generation rate. So that's where these terms come from. Okay, and finally we have the diffusion equation for energy transport. We replace the gradient of temperature with a gradient with respect to the mass coordinate, with the Lagrangian mass coordinate. This gives these 4 pi r squared dependencies. So there are these 4 pi's are hidden, r squared are hidden here. And we replace the flux by the luminosity. This gives another 4 pi r squared, and we are left then with the expression on the right hand side, which tells us dt by dmr with respect to the Lagrangian variable is proportional to minus the luminosity, and the essential quantity which is entering here is the opacity here on the right hand side. Of course, we have ignored convection here. This is just for radiation diffusion. To complete the system, well, there are if we include nuclear processes, then we have to take into account the change of mass fraction. Here, the time derivative is a Lagrangian one, which is a function of the mass fractions of all nuclear species which take part in the process, and the pressure and the temperature. So this equation is essentially not changed if we want to take it into account. Okay, like before, equation of state, the nuclear energy generation and the opacities have to be taken from atomic and nuclear physics. Okay, that's the complete system. I hope I didn't forget. Okay, this is the equation which we have to solve, both for the stationary structure of a star and for the dynamics of a star. Now, if you look at these equations, there are time derivatives appearing here and on 3 places. One of them is the mechanical acceleration, which contains this time derivative here. Well, this is mechanics, so it should be associated, of course, with one of the typical stellar timescales. And the mechanical timescale, or the shortest timescale which we know of, is associated here with the loss of mechanical equilibrium. So this derivative is associated with the dynamical timescale of the star. There are 2 time derivatives appearing here, maybe written as a single time derivative of the entropy here. This has to do with the change of the heat content of the stellar matter. So this is related to the thermal timescale or the Kelvin-Helmholtz timescale. This is the green ones. And there is a third appearance of time derivative here. This has to do with nuclear processes. So the timescale which enters here is the nuclear timescale. So you recover the time, once you're looking at the system of equations, you recover the 3 timescales which are important for stellar structure and evolution. Okay, once we are interested in pulsations, then of course we have to consider, or we must not ignore this term. This is important once we are looking for stellar pulsations. On the other hand, if we are looking for a star in hydrostatic equilibrium, then we simply drop this term. Stellar equilibrium means the gravity is balanced by a pressure gradient. And this is called hydrostatic equilibrium. If we consider a star in equilibrium, then we usually drop this term. This is done in stellar evolution. Stellar evolution assumes that the star is in hydrostatic equilibrium. So we drop this term and only consider the green time derivatives and, of course, in particular, the blue ones. So stellar evolution, thermal timescale plays a role and the nuclear timescale plays a role. And the dynamical timescale is we get rid of the thermal timescale by simply ignoring the acceleration here. On the opposite, if we are interested in stellar pulsations, what we do? Well, stellar pulsations occur on a timescale which is much shorter than the thermal timescale and the nuclear timescale. So we may ignore, be careful, it's not completely true, but we may surely assume that nuclear processes don't take place or are not important during one pulsation period. It just takes too long for them to operate, so we can ignore nuclear processes once we are considering stellar pulsations. We assume that the mass fractions of our species are constant. And in some cases, we even can assume that epsilon is 0. We do not consider the energy generation because nuclear processes are too long on timescales which we are interested in, which are very short, which are at most a few hundred days, compared to nuclear timescale of 10 to 10 years. We can assume everything is constant. The same is true partly. We will come to that. We can partially assume that these terms are 0 once once we consider pulsations, when can we really assume that this term is zero? It is the time derivative of the entropy. So once we ask for situation when this term can be regarded as zero, what would be once we assume that the changes during pulsations might be adiabatic. One has to check this, whether it's really true that we can assume that this term vanishes, that we have adiabatic motions. We'll come to that. It's not always true. For pulsations, partially we have to take into account this term, but there are stars where this term might be ignored. For instance, for the Sun, it's quite perfect to ignore this term. You get perfect results. There are other stars which also are close to adiabatic changes of state, but there are stars where this is no longer true. We'll come to that later on. So once we do stellar evolution, we ignore the red term. The red term, in any way, we consider only these long timescales, thermal timescale, nuclear timescale. For pulsations, we have to take into account the dynamical term, and partially we take into account the change of heat content, the thermal timescale. We can ignore the nuclear timescale. Okay. So contained in this system of equation are also the equations of stellar evolution. It covers both, of course, radial symmetry is assumed from the beginning. It assumes stellar evolution that is usually done in a spherically symmetric way. So these are the equations of stellar evolution, and these are at the same time the equations which we have to solve once we consider radial pulsations. The difference is just ignoring one or the other term, one or the other time derivative. Okay. Yeah, that's it. Okay, we have done this already. So, well, I was told you might not be that familiar with stellar evolution. So what we are doing now is, having arrived at these equations, which may also be used for stellar evolution, we make a short digression on stellar evolution, and we will consider some of the basic facts in stellar evolution. This is, on one hand, necessary for understanding how a stationary stellar model looks like, and we use static or hydrostatic equilibria as an initial point for studying stellar pulsations. So stellar pulsation studies always start with a stellar model. The stellar model might be taken from stellar evolution, or might be has to be taken from a consideration of these equations with the accelerations having been put to zero, and that's the starting point. So in that sense, it's useful to get some information about stellar evolution, and therefore we make a short digression on stellar evolution. Questions? Yes.
Yes. Yeah, so while introducing different processes like diffusion and convection, I observed that you took the assumption of opacity.
Yeah.
Why is it required?
Okay, it's not an assumption. It's a we describe in the process of energy transport in terms of a diffusion process. And so we have flux is proportional to minus the gradient of the temperature.
No, sorry. Let me rephrase. My question is different. Opacity was introduced later. Yeah. I remember now. Optically thick.
Yes.
Optically thick. Why?
Well, you could also consider the optically thin part of the star, but what is usually, well, there are two types of astronomers. The ones which deal with the atmosphere of the star, and ones which deal with the interior of the star. Okay. And the domain where these two guys operate is cut or is confined by the photosphere. Anything that lies below the photosphere is the subject of stellar interiors, and anything above is to those guys with stellar atmospheres. And once we do stellar evolution, this is usually done is everything below the photosphere. So the photosphere is for those people dealing with stellar interiors, and also for those who do pulsations, is the outer boundary of this domain is the photosphere. Well, it would be nice if we could extend also to the optically thin regime, but then the equations of radiation transport become very, very complicated. And just to refrain from having to deal with the complete radiation transport, people usually restrict themselves to regions below the photosphere where the radiation transport can be done by a diffusion approximation.
Thank you.
Actually, this is a problem because the photosphere, for those doing the interior of the star, the photosphere is not, it's just the outer boundary of the model, but it's not the outer boundary of the star. And so what do we need to assume as a boundary condition at the photosphere for the interior? It's ambiguous because it's not the physical boundary, and there are several good arguments which should be the boundary conditions there, but in principle they are ambiguous, and you cannot say, well, you have no strict mathematical way to prove which is the correct outer boundary condition. It's a problem. It occurs with the boundary conditions because, well, it's exactly what you addressed in your question. You should take into account both the interior of the star and the atmosphere.
One more follow-up question. So when this pulsation is happening, so since you said that optically thick is within the photosphere, right?
Yes.
So is there possibility of lag between the contraction of the star and the photosphere also?
Yeah, we even have the problem in a pulsating star. In a static star, it's quite okay to put the photosphere where Stefan Boltzmann's law is valid. Okay, but if the star starts to move, then also the photosphere will move, and it will move, and it will not only be at the previous outer boundary in the Lagrangian sense, but it could move within, or could move to another Lagrangian position. And we do not exactly know where and how to define the photosphere then. So this is a problem once we come to a time-dependent pulsating star. Does it? Okay, it's a problem. I agree. Okay. Okay, now let us start with stellar evolution, with a small digression on stellar evolution. So I have to. Okay, well, stellar evolution, as we already learned, is governed by the equation of spherical symmetric structure and dynamics, with the additional assumption that we have hydrostatic equilibrium. That means the acceleration term is zero. The pressure gradient is balanced by gravity. This is the mechanical equilibrium. Well, the relevant time scales are thermal and nuclear. That's we already seen, and stellar evolution typically occurs on long time scales, which are not accessible to human beings. 10 to 7 years, 10 to 10 years. It's not accessible. So what we cannot follow the stellar evolution, which we calculate by numerical integration, for instance. It proceeds on timescales of 10 to 7 to 10 to 10 years. So how do we compare it with observations? Well, we have to, concerning a comparison with observation, we have to keep in mind what we see on the sky is never the evolution of the star. We see different stars at a different stage of evolution. So we see what we see in a star is a snapshot of the evolution at today's time, plus minus 10, 20 years. So we see snapshots, and we have to connect all these stellar stars which we see in the right way, so to give you the trace of, or put them on an evolutionary track of which you calculate and put them at the right position. So it's the comparison of the theory of stellar evolution is done by taking a huge big amount of observation, huge big amount of stars, and keeping in mind these are stars at the different stages of evolution. They may have had different initial masses, and now we put them together and try to get a picture which relates to the stellar evolution, where we follow a single star along its evolution on timescales of 10 to 7 or 10 to 10 years. So it might be in sometimes rather complicated where to put a star. What is the evolutionary stage of a star? It's sometimes pretty difficult, but this is the only way we can proceed, because we do not have access to these very, very long time scales. Okay, so this is the basis of what we are considering here. Well, I have listed here some literature about. There are many more books here. I have taken pictures and figures mainly from Bowers and Dieming, Kippenhahn and Weigert. Kippenhahn because he was the one who initiated the stellar structure and evolution lecture in Göttingen at my home university, and well, this is so to say tradition to have this lecture there. Actually, it's quite reasonable book. Well, just if you want to have further reading, and then of course there is a pretty old but still very good, physically very good book by an Indian, Chandrasekhar, which is an introduction to the study of stellar structure. Okay, there are some other ones. If you want to know anything about stellar structure and physics of stars, you should go to Cox and Julie. You can never read this book because it's that thick. It's just for consulting. If you want to know some physics about a particular problem, go to this book. You will find everything. Okay, this is but you can't read it as a textbook. It's impossible. Okay, so what we'll do now for the next few lectures is we will briefly comment on stellar parameters. Then we need to discuss, this is also necessary for later use, we will discuss the equation of state in more detail. We will have to discuss the opacity. This is very important for stellar pulsations. We will comment a little bit on nuclear burning and the energy transport, because that touches also some problem which appears again in stellar pulsation theory. The stability of stratification, energy transport, stability of stratification comes in again if you consider G modes later on. So we have to deal a little bit with that, and then we'll briefly show how the evolutionary tracks proceed in the Hertzsprung-Russell diagram. And then I would like to comment on some very basic elements of stellar evolution, which is the virial theorem, which will also be addressed in in one of the tutorials, the mass luminosity luminosity relation, and then the effect of degeneracy. These basic elements are maybe connected with the basic questions we may have once we consider stars. For instance, well, if we look out of the window, we see the sun is shining. So one naive question would be, why do we see the sun shining? What is the reason, the physical reason that the sun shines, that the sun gets energy or puts energy to us on the earth? So what would be your answer to this question? What could be the answer to that question? Why does a star radiate? All stars radiate. The sun radiates. We live from that. Why does a star radiate? What is the reason? How would you answer that question? Some suggestion. It doesn't need to be wrong. It doesn't need to be right. A source of energy. Okay, there is a source of energy. That's the reason. Let's keep that in mind. Another pardon? I haven't understood. Nuclear fusion. Yeah, okay, nuclear fusion. Yes, I think this should be on the same direction. Nuclear fusion, energy production within the star. Okay, let's keep that in mind. This is one of the basic questions of which you would ask. Actually, I expected this answer, and I can, in anticipation, I say it's not correct. There's another reason for a star to radiate. But keep this in mind. It's a very intuitive answer, and it seems to be plausible. Everybody would say this, but if you know a little bit more about astrophysics and stellar physics, the answer is a little bit different. So keep it in mind. So we will come to that, and we will see why a star radiates. This is one of the questions which we try to solve. And another question would be, why does a star evolve, and how does it evolve? The main question, or the essential question, is, why does a star evolve? Why cannot it stay forever as it is? Why does the star have to evolve? These are the questions which I like to somehow address as some basic elements. And this will continue, or this will contain then some physical arguments how we can answer and how we have to answer these questions. We have to stop? We have to stop, or is there some time left? Okay, so let's continue here this afternoon.